night was to take your example 3 data where you had done 2 teams, go get 2 more teams worth of data, right? But rather than calculate mean and standard deviation by hand with so many pieces of data, there was how to do it on the calculator or some sites you could go to that would do it for you, right? Okay, so can somebody just tell me how their mean and standard deviation turned out? And we'll use yours as an example. So somebody with their 4 teams of data, you entered it in the calculator. Michelle. Okay, so we were looking at heights of baseball players, okay? So she's saying the average height of the players she looked at was 74.2 inches, okay? Which is how tall? 6'2", okay? And the standard deviation was 2.2 inches, okay? Which kind of just tells us how spread out the data is. It doesn't really tell us yet until we understand a little bit more about normal distribution. Ashley, you had your hand up too. What was your mean? Out of curiosity. And what was your standard deviation? 2.2. So 73.9 and 2.2, right? And you guys didn't do the same 2 teams. You didn't talk to each other, right? Okay, did anybody else have a number for us that they're willing to share, a mean and a standard deviation? Ben? Okay, 74.1 and 2.45. Lauren? You got the same exact thing as Michelle. Jason?
I got for the mean 74.22.
Okay, then a 2.24. So are we okay with accepting this as a mean and standard deviation? Probably if we did all the data, it might adjust a little, but you guys can see. So why do you think your data was so close, even if you guys chose different teams? Savannah? Okay, so that baseball players generally are within a small range of heights, right? What else would contribute to us having data that's super similar and draws very similar conclusions? Jason?
They're all like part of the same group as well. Like they're all baseball players and they're all males.
Okay, they're all males. They're all baseball players. Ashley, is that what you were going to say, or did you have something else? Good. Okay, so they all use 4 teams. You might have overlapping data and just the pure number of pieces of data, right? How many pieces of data did you have? Like about 100. So do you think you did a pretty good sample of the entire population of baseball players? There's a lot of teams, but 100 pieces of data is a pretty good chunk. So that's probably why our information was there. If we had just each looked at 1 team, we might have gotten more different answers, because 1 team might have a couple of short players on it or a couple of tall players on it that skewed your data compared to somebody else's, okay? So then you created a histogram on the calculator. Explain to me how your histograms looked shape-wise. Savannah? Yeah. Was relatively low. Do you want to come draw it? Is that okay? Yeah. I wish I had a dock camera. I would just. No, it's fine. It's fine. Oh yeah, that's good. Yeah. You don't have to draw the exact, like how high the bars went. Just draw the general so they can see the shape of it. No, it's okay. Just draw the bars so they can see the. No, you don't have to hold anything down. Just hit the press. Crazy, huh? Here, I'll move this first. Awesome. Thank you. All right. So how would you describe the shape of the distribution? Michelle? It's pretty normal, right? would you expect height distributions to be normal? Yes. Okay. So it makes sense that they're normal in what we know, like in our society, okay? And it looks normal when we're looking at the 100 pieces of data, okay? So does the data appear to be normally distributed? Yes. Okay. So then it says sketch a normal curve. So here's what a normal curve would look like. Okay. It says with the x-axis labeled with heights that represent the mean and each height within 3 standard deviations above the mean and 3 standard deviations below the mean. So what that means, to mark on here where the mean is, here's the x-axis, right? Where would the mean be with respect to the curve? Kenny, so you already talked. Good, the highest point on the curve. That's what we talked about with normal, right? Mean, median, and mode kind of all in one place. So I would expect this part on the x-axis to represent my mean, which in this case was 74.2 inches. Okay. Then it said to also label up to 3 standard deviations above the mean and 3 standard deviations below the mean. Okay. So 1 standard deviation is 2.2 inches. So if I was 1 standard deviation above the mean, it would be this way on the x-axis. And what would the numerical value of height be that's there if I'm exactly 1 standard deviation above the mean? Ben? Good, 76.4. Okay. And then the next standard deviation above the mean would be at what? Penny? 78.6. Do you guys notice what we're doing? We're just adding 2.2 each time. Okay, why 2.2? Because 2.2 was my standard deviation. Okay, except for that should say 8. Okay. So when I go standard deviations to the left or standard deviations below the mean, okay, this would be 72. Okay, this would be 69.9, right? Yes. No. 69.8? Yeah. Okay. Can't do math today. All right. And then 67.6. Are we okay with that idea? So you would all have something like this. So why would we want to sketch this? So people found that when things are normally distributed, there was something standard they could say about everything that falls into that type of distribution. Certain amounts of data are in certain places. Where is most of the data? Lauren? Located in the center of the graph. So what they like to say is 1 standard deviation from the mean, so like from here to here, that means 1 above and 1 below, captures most of the data. Would you guys agree with that? Okay. Then they say 2 standard deviations from the mean captures almost all of the data, right? And 3 standard deviations from the mean is like everything except for a very, 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 very small amount. Would you guys agree with that? Things that are normally distributed. It turns out not only could they come up with this, but based on looking at things that are normally distributed, there's something called the empirical rule that tells you exactly how much of the data, if something's normally distributed, falls in those areas. Okay, so we're going to write down that empirical data, and that's what makes working with normal distributions interesting for us, because then we are able to know a little bit more about the distribution than we would know if it wasn't normal. Okay? So the empirical rule is basically, these numbers. So this is in your note guide. 68, 95, 99.7. What those numbers mean are percentages. Okay? So this is what it means. 68% of the population is within 1 standard deviation. Okay? So remember how I told you guys if you went 1 standard deviation each way, you got most of the data? We don't even say most of the data. If it's normally distributed, we know exactly how much of the data falls in that curve. 68%. So if baseball player heights are really normally distributed, then 68% of baseball players fall between those two heights that we marked as this one standard deviation away from the mean on each side. Okay? Then what do you think the 95 stands for? Yeah, so 95% of the population, okay, is within 2 standard deviations. So go out a little further. You don't just have the majority of the data, you have almost everybody, right? 95% of people. 99.7% of the population is within the 3 standard deviations, okay? Meaning everybody but this small extreme percentage, those outliers of the population are captured by the time that you go 3 standard deviations away. This is not true with every data set. This is true with data sets that are normal. Okay? Does that make sense to everybody? Okay. So we're saying then that here we capture 68% of the data. Okay? So then this kind of become like little arithmetic puzzle problems. If 68% of the data is captured within one mean, or one standard deviation in each direction of the mean, how much of the data is one standard deviation above the mean? How much of the data would we capture that way? 34%, okay, on each side. Okay. And if we're saying that 2 standard deviations away is 95% of the population, what percent of the population is falling between the 2nd and 3rd standard deviation? Savannah? Okay, so let's check it. So first of all, we can subtract out the 68 because we've already marked that, right? So 95 minus 68 is 27. Okay? That means there's 27% of the population if we count both of these areas, right? So then if we cut the 27 in half, we get 13.5. So 13.5% of the population is here. 13.5% is here. Okay? Now, if we've captured 95% of the population so far, okay, 3 standard deviations captures 99.7. So what is the amount of people that's between the 2nd and 3rd standard deviation in total on both sides of the mean? What's the difference between 99.7 and 95? Yeah. Okay, so 4, yeah. So 4.7 is the difference, right? So there's an extra 4.7% captured in total when we go out the 3rd standard deviation. Half of it is above the mean and half of it is below. So if we take that 4.7, okay, and divide it by 2, we get 2.35, right? So this is 2.35% of the population. What percent of the population is more than 3 standard deviations above the mean? So what percent of people end up way out here? Zach? Good. Okay, so how did Zach get 0.15? What percent of the population is left is within 3 standard deviations? We've covered 99.7% of the people. 0.3, right? But 0.3 is the extremes over there and the extremes over there. So 0.15% are the extreme over there and 0.15 are the extreme over here. Okay? So just a little reminder, we used, because we're going to need this on the next thing, for baseball players, Unless you have your own. If you have your own, you have your own information. If you don't have your own, we used a mean of 70. I have to check it. 70. Sorry, we used Michelle's. It was 74.2 and 2.2. Okay, so we used a mean of 74.2 and a standard deviation of 2.2. So knowing the empirical rule and how this stuff works, okay, I want you to write in 3 statements on your paper based on the data you collected. Okay, right here is just some vocabulary if you see it used and some symbols that you might see on the calculator and stuff like that. Okay. So notice, like, we're usually dealing with a sample, right? We're not putting every baseball player into the calculator. We put 100 of them, okay? So we dealt with a sample, and so P is like our population proportion. X would be elements, our sample elements, and N, okay, would be our population, little n, our sample size. So they're saying, like, the capital letters mean, like, for the entire population, and the lowercase letters mean for your sample. So you would usually be using lowercase letters unless you've tested the entire population, okay? And then this letter you might have seen pop up on your calculator when you ran some of the statistics. That is the mean if you've tested the whole population. The X with the bar over it that we already determined was mean is for a sample. So they use 2 symbols lots of times to represent the same thing. But that's because in statistics, you need to tell somebody whether you just did a sampling or you actually got the whole population and ran the statistics, okay? So what I want you guys to do right now is based on your normal curve, okay? If you don't have your own normal curve, then you're going to base it on Michelle's, okay? A mean of 74.2 and a standard deviation of 2.2. And we went and sketched it. What percent, make 3 statements based on the rule we just talked about, the 68, 95, 99.7, okay, the empirical rule. 68% of Major League Baseball player heights fall between blank and blank, okay? 95% of Major League Baseball heights fall between blank and blank, okay? 99.7 of heights fall between this and this, okay? So take a minute to fill that out. All right, and before we decide what the scores mean, I'm going to show you guys a couple resources and let you guys Google on your devices how a z-score is actually calculated, and we'll see if Kenny's idea is right about just kind of extending this idea of percentage within the standard deviation that they're at. So we're going to let you guys look on your devices to see if you can find the formula for z-score, and then if you can find what does it mean to have a z-score of 1 and what does it mean to have a z-score of negative 1.3. In addition to using devices where you're looking that up, in your note guide, there is another beautiful table. No, you don't have to memorize the table, okay, but it's a tool. This is a z-score table, okay, and this is the z-score. Like if my z-score was negative 2.81, this would be, okay, something, 0.0025. The picture is telling you what they're supposed to be telling you, okay? But I'm going to let you guys look at it a little more. So you can look at the chart you have in your notes, at what the different z-scores are and what the picture says it's measuring. And then in addition to that, you can look on your devices. I'll give you guys about 3 minutes, and we'll see if you came up with how do you calculate a z-score, and based on that chart, do you understand what it means to be a z-score of 1 versus a z-score of negative 1.3. This will not do what I wanted to do. There we go. Like this. Okay, and then divided by what? All right, so these were the Greek symbols. Okay, so what is it really saying to do with those symbols? Savannah?
Take the mean and subtract a data point.
Okay.
Point, and then divide by the standard deviation.
Okay. So it's kind of what Kenny was saying, right? You're kind of looking at a ratio. You're saying, how far is this piece of data from the mean divided up by the number of standard deviations, and it's giving us a score. Okay? So what does it mean? When I get a z-score of 1, so let me go back to my z-score table. So the positive ones are here. Okay. get a z-score of 1, meaning 1.000, I get 0.8413. What is 0.8413 telling me? See, Penny, see Savannah. Zach? So it's not necessarily the standard deviation. Yeah. Okay, so it's kind of giving me a probability or a percentage or like the area under the curve. See the picture right there? Okay? You're marking it, and basically what this is telling you is underneath that normal curve, if you have 100% of people, or 1 when you don't write it as a percentage, right? This score is above that much of it, okay? See the shaded area, how it's below the score? So it's always giving you basically how much of the curve is shaded below that score, okay? So if I have a z-score of 1, 84.13% of the curve is shaded below me. In other words, the probability, okay, well, not probability, we'll do just area shading right now, or percentile. I am above 84.13%. Okay, that's where I'm at in the curve. Does that make sense to everybody? Okay, so a z-score of 1, you can write this into your notes, gives you that 80.8413 is your area underneath the curve, okay? Or it's above 84.13%. Okay? So it's kind of like the standard deviations, but instead of just giving you the 68, 95, 99.7, it says you can give me any one person's score and I can tell you exactly where they are instead of just saying they fall within this many standard deviations, which is what you guys wanted, right? You wanted to know exactly what they are. The cool thing is, too, you can take scores from different things, SAT, ACT, but when you convert it to a z-score, they're going to tell you the same thing. You can now compare their actual percentages, but you couldn't compare their percentages on the tests because they are different, okay? So look back at your problem now, okay? And now decide, okay, oops, back to your problem. Okay, sorry, my PowerPoint is too low. Okay, so now based on your test score, who would you choose and why? Okay. Okay, student A, what was their z-score? Jason? 1.509. Okay. Student B, what was the z-score? 1.413. Good. Okay. So who scored higher than more of the population? Student A. Okay. So some of you guys figured that out, like Jason was talking to me about. He kind of just got to that place where he knew it was however many standard deviations and then kind of compared the scores to that standard deviation marking. That's essentially what you're doing, but this is the formalized way that everybody would understand in the world of statistics how we're doing it, and we'll do that every time. Okay? All right. So okay, so male heights in the U.S. have a normal distribution, okay? Approximate mean of 70 and standard deviation of 3. Female heights have a normal distribution with a mean of 64 and a standard deviation of 3. So based on this, what is your z-score in your gender, okay? And what is your percentile within your gender? So for example, I think that I am 5'10", okay? So if I am 5'10", okay, then I am 70 inches tall, okay? So if I'm 70 inches tall, my z-score, since I'm female, okay, 70 minus what they said is the mean of female heights, which is 64, divided by the standard deviation of female heights, which is 3. Okay. Oh, I can do this. Did you see? I went to go get my calculator, but 70 minus 64 is 6, right? And 6 divided by 3 is 2. Okay, so my z-score happens to be 2, okay? Which, if I look it up on that chart, 2, okay, 0.9772. That shouldn't be that surprising of a number considering my z-score was exactly 2. Because what is that really saying? How many standard deviations am I away from the mean? Exactly 2. What the z-score is allowing you to do is when somebody's not exactly 2 standard deviations away from the mean, it's letting you figure out exactly how many they are and then telling you what that calculates as a percentile. So notice mine is going to be 97.7. That's actually not that surprising because I'm exactly at the 2 mark, and that was in our empirical rule, right? So, my z-score is 2, okay? And so my percentile within my gender would be 97th percentile or 97.7%, something like that, okay? So, do we feel like tonight we can do problems that require you to just take a normal distribution and based on standard deviation say, oh, this much of the population falls here, just knowing your 68, 95, and 99.7 rule? Then beyond that, if I want to know the percentage that somebody is or percentile or the probability of picking them, right? Okay? Or the probability of picking someone that is my height or below is 97.7%. That's a female in the population, okay? Can we do that by converting it to a z-score and looking at the table? You'll need the z-table. If you don't have the z-table, you can get one online, okay? You can just z-score table. They'll come up, okay? Believe it or not, they exist out there. Or if you open the note guide, towards the end there of the stats section, you have your z-score table, okay? So tonight's homework is going to be the normal distribution worksheet. And if you guys were quick on checking the block spot worksheet, it was the wrong one. And now you know why it was confused, okay? Seemed like you knew nothing about it, and now you'll be able to do that whole thing.